Hi, in this presentation, we're going to talk about energy. So, as we look around the universe, everything in the universe is either constituted by matter or it's energy. And energy can change the condition of matter, and energy can also do work. And energy can come in many different forms. It can be mechanical, electrical, radiant, or nuclear. But in this presentation, we're going to concentrate on mechanical energy. But before we get into the details of energy, we have to understand a couple things about work and power. And let's talk about those concepts for a minute. So, work involves force and distance. And if we want to have an equation for work, we can say work equals force that we applied to an object multiplied by the distance we moved that object. So, to have work, we have to have the application of force, and we have to have some type of matter or object moved by that force. So let's look at our workers here and say if our workers are lifting their load up to one story, they're doing a certain amount of work. And we can say that that work is one force needed to lift one object times one distance up one story. But now let's say the workers are pulling that same load up two stories. Now they're doing twice the work because we still have the force of one on the one object, but now we've doubled the distance. So work would be F times 2D. And what if we lift twice the load? Again, now we're going to do twice as much work because we need twice as much force to lift the load twice as far. So going back, if we have our work that our workman is doing is one force times one distance to lift one bag that high. If he's lifting two bags, it's going to be work is two forces times distance. So we're going to see it's going to be double the work. But remember, to have work, we have to have matter covering some kind of distance. So let's say this weightlifter has lifted her weight and she's holding the weight steady over her head. Is she doing work right then? And the answer is no. If the barbell isn't being moved by her, if it's stationary, even though she's holding it up, we can say there's no work being done on the barbell. But now, when she's in the process of lifting the weight off the floor, yes, now she's doing work because she's exerting a force and she's moving that mass of the barbell a certain distance. So we can categorize work in basically two big categories. There's work that we're doing against another force. So think if you're pulling a bow, as you pull back on the bowstring, you're actually pulling against the strength of the bow. Or think about when you're working out and you're doing push-ups. When you're doing push-ups, you're pushing against the force of gravity that's pulling your body weight down. We can also do work to change the speed of an object, such as speeding up or slowing down a car or hitting a golf ball to make it go from a zero momentum on the tee to quite a fast momentum as it's moving. So work is measured in Newton meters or joules, and 1 joule equals the force of 1 Newton exerted over a distance of 1 meter. So for instance, we could say we have an apple, and if you lift that apple over your head as far as your arm will stretch, you've exerted um, the force of 1 Newton over about a meter, and so you've done about 1 joule of work. But that's a pretty small amount of work. So usually we're going to use, when we're talking about larger values, we're going to say kilojoules, which is thousands of joules, or megajoules, which is millions of joules. So thinking about work, let's look at this problem. So we know we do work when we lift a barbell. How much work is done in lifting a barbell that's twice as heavy the same distance? Would you do twice as much, half as much, the same, or depends on the speed of your lift? Well, we know when we're calculating work, all we're looking at is the force applied and the distance something is moved. So the speed really doesn't matter. So, but if you're lifting twice as much, exerting twice as much force over the same distance, you're doing twice as much work. So A is the correct answer there. So our definition of work tells us how much force we're applying and over what distance. But what if we want to know about the time? So here's something to think about. Let's say you went to the grocery store and you have to make two trips to take the groceries to your apartment up one flight of stairs. All the bags weigh the same, but you might notice if you walk up taking the groceries on your first trip, but then on your second trip carrying the same mass of groceries, you run up the stairs, you feel more tired. And that's because you ran up the stairs and you took less time, and so you used more power. Power tells us how fast work is done. And so if we wanted to express it as an equation, we could write it as power equals the work done divided by the time interval. So let's look at power in a slightly different way. So let's say you and your friend both sign up for a marathon and you both have 60 kilograms of mass. So it's going to take equal force to move your bodies the 26 miles. But on the day of the marathon, you decide to walk the 26 miles, but she runs the whole 26 miles. So who would you say did more work? Well, if you said you both did the same amount of work, you're correct because remember you both have the same mass. It's going to take the same force to move that mass. So, and you're covering the same distance, 26 miles. So you're doing the equal amount of work whether you walk the 26 miles or you run the 26 miles. But now let's talk about who used more power. And of course, the correct answer is your friend did because she did the work in less time. So she used more power. So let's look at two engines. And engine B is twice as powerful as engine A. And this tells us that engine B can either do twice the work of engine A in the same time, or engine B can do the same work as engine A in only half the time. The unit of power we use for the unit of measure we use for power is the watt. And the watt is equivalent to 1 joule of work done in 1 second. And again, that's a kind of a small amount of power. So most of the time when we're talking about power, we're using kilowatts, thousands of watts, or megawatts, millions of watts. Um, and then engines here in the United States are often measured in horsepower. And that's a kind of an archaic measure when combustion engines were first introduced and they wanted to measure it to something people were familiar with, and people were familiar with horse-drawn vehicles. So we still have horsepower in use. And 1 horsepower is equal to about 746 watts. So now that we've talked about work and power, we can go back to energy. And I told you that we're going to concentrate on mechanical energy in this presentation. And mechanical energy can either be due to the position of matter, or it can be due to motion, or both. And when we talk about the position of matter and the energy due to that, we call that potential energy. Potential energy can be in several different forms. The first form that potential energy can be in is chemical energy. And this is due to the position of matter at a molecular level. And it has a lot to do with the electrical charges within and between molecules and what happens as those relative positions are changed. So, chemical energy is stored in our fossil fuels such as oil, coal, and gas. We can have potential energy stored chemically in batteries. And we have our potential energy also chemically stored in our food before we eat it. Another type of potential energy is gravitational, and this is a potential energy due to the elevated position of matter. So think about, we might have water that's kept in an elevated reservoirs in this picture here. And if you think about the thousands of kilotons of water that's being held up pretty high, you can see that's a lot of potential energy that we can use by releasing some of this water and using it to power, say, turbines to generate electricity. Also, you can think about the raised ram of a pile driver, or even a hammer in your hand as you have it up before you bring it down to hit a nail. So that's due to the force of gravity. And this gravitational potential energy is equal to the work done, the force times distance, in lifting that matter against gravity. So we can write that as potential energy is mg, which of course is the force of gravity against mass, times the height that we lifted this object. So let's look at this picture. So we have a 10 Newton ball and we've lifted it 3 meters. Okay. Is the work done the same in all three cases? And is the potential energy the same? And the answer is yes. In each case, we have a 10 Newton ball lifted to a height of 3 meters. Okay. Whether we lifted it all in one go or we lifted it 1 meter at a time 3 times, or if we pushed it up a slope, because if we push up a slope, we don't have to push the whole 10 newtons. It's usually about 6 newtons on this type of slope. So yeah, so the work we did, the force times the distance, is all the same. And the potential energy is the same because after we get the ball up to the top, it's raised 3 meters. So its potential energy, the height we've lifted it 3 meters versus the pull of gravity on the 10 newtons, is going to be the same. So it has the same potential energy. Now that was potential energy. Now let's move on to kinetic energy, which is the energy of motion. And anytime an object is moving, it's capable of doing some work. And the amount of energy and the work it's capable of doing depends on the mass of the object and the speed of the object. So our kinetic energy is equal to the mass of the object multiplied by the square of its velocity. And then we're going to take that number and multiply it by 1/2. So if we wrote it in an equation, we'd have kinetic energy equals 1/2 of the mass times the velocity squared. So kinetic energy allows an object to do work, and this will be equal to the work required to bring the object from rest to that speed. So in equation form, the net force times the distance, which should sound familiar, is equal to the kinetic energy. So as we have written, kinetic energy is 1/2 of the mass times the velocity squared. That's exactly the same as writing the work, net force times distance, is equal to 1/2 the mass times the velocity squared. So if we have a car with momentum, does it have kinetic energy? And would you say A, yes, due to motion alone, B, yes, when the car is accelerating, C, yes, when the motion is unchanging, or would you say no, it doesn't have to have kinetic energy? Well, the correct answer here is A. Yes, the car does have kinetic energy just due to the fact that it's in motion. Whether it's accelerating, decelerating at a steady rate, as long as the car is moving, it has kinetic energy. So knowing that our kinetic energy is equal to the work, the force times distance, equals 1/2 the mass times velocity squared, what would happen if we doubled the speed? Well, since the speed or the velocity is squared in our equation, if we double the velocity, the kinetic energy is going to be quadrupled. So it's going to take 4 times the work to double the speed of a moving object. So we can say, let's say, for instance, we had a mass of 3 kilograms and it's moving at a velocity of 2 meters per second. Well, we're going to square that 2 meters per second. So now our 3 kilogram mass is going to be multiplied by 4, which is 2 squared, and we get 12. And half of that is 6. So our kinetic energy would be 6 in that case. But then if we go and we double the velocity from 2 to 4, well, now 4 times 4 is 16 times our mass, which was 3 kilograms. So now we have 3 times 16, that's 48. And half of 48 is 24. So our kinetic energy is 4 times what we had before. So talking about kinetic energy leads us into the work energy theorem. And this theorem basically says that the gain or reduction of kinetic energy is a result of work. So in equation form, we can say the work equals the change in kinetic energy. And so we can write that as work equals that delta symbol means change in kinetic energy. Or we can write it out with all our variables. Our force times distance, which is work, equals the delta change in 1/2 mass times velocity squared, which is our kinetic energy formula. So, and of course, work on this equation is based always on net force. So think about this. If we are pushing on an object and friction also acts on the object, the net force is however much force we're pushing minus friction. And that net force is the only part of the work that's actually changing the kinetic object that we're pushing. So, but we're exerting more force to overcome that friction to get that net force. So where does the rest of our work go? Okay. And the rest of that force is it's not being lost, it's being transformed into heat by the friction. Which brings us into our next concept, the law of conservation of energy. And this says that energy cannot be created or destroyed. And you might say, well, how can that be? Because, I put gas in my car and all of a sudden it can go. Well, yeah, we can't create energy, but we can transform it from one form into another. So we can take that gasoline, that potential energy in that gasoline, and transform it into the energy that drives your internal combustion engine and your car goes. So we can transform energy from one form to the other, but the total amount of energy never changes. And let's look at the example in our picture here. So we can have potential energy with our weight hanging there on from its pulley. But then once we cut the supporting rope, now all of a sudden that potential energy is changed into kinetic energy. Okay, so our potential energy didn't disappear or it wasn't destroyed, it was just transformed into kinetic energy. So let's look at this man drawing his bow. When he draws the bow, he's doing work on the system and giving it potential energy. The potential energy is stored in the bow. So he pulls the bowstring, the bow is curved, and that compresses the atoms on the inside of the curve. And that's where that potential energy is stored. When he releases the bowstring, most of the potential energy that was stored in the bow is now transferred to the arrow as kinetic energy. But again, it's not 100% of the potential energy. Some of the energy is going to be transferred to the bow as vibration and heat. And if you've ever wondered why uh, competition archers have these kind of things sticking off their bow, like here, those are actually to soak up some of the vibration that is transferred to the bow by that extra energy so that it doesn't shake the archer's hand. So we can have machines that can multiply forces or change the direction of those forces. Now, again, machines can't create energy, but they can transform energy from one form to another, or they can transfer energy from one location to another. But again, they can't multiply work or energy. There's no way to get more energy out of a machine than you put into the machine. And this is also uses the conservation of energy concept that our work input is pretty much going to equal our work output. So we can say our input force times our input distance is going to equal our output force times our output distance. Or we can write it in this equation here, force times distance input, force times distance output, which is basically three ways to write the same concept. The simplest machine we can encounter is the lever. And the lever is a device that rotates on a point of support, which we call the fulcrum. In this picture, it's the little triangle here. And the lever allows us to apply a small force over a large distance. So like right here, we apply a small force on a large distance. And then through the fulcrum, that's transformed into a large force over a small distance. And we can also do it vice versa. If we applied a large force moved at a small distance over here, we would have a small force moved a large distance over here. So there's three types of levers that we can encounter. There's a first class lever, which is like we saw in the picture previously, where the fulcrum is in between the force or effort in this picture and the load. And an example of a lever like this might be a seesaw that you would see on a child's playground. So one child sits on this end and puts the effort in, the other child is the load, and the fulcrum is in between them. A second class lever means the load, the weight, is in between the force over here and the fulcrum. And this would be like a wheelbarrow. With the wheelbarrow, the fulcrum is over here by the wheel, the load is in the bucket of the wheelbarrow, and we expend the force over here on the handles. And then the third class of lever is where the fulcrum is way over here, the force is applied in the middle, and then the load is at the end. And you can think about this as your elbow is an example of a third class lever. So think about the fulcrum is the actual elbow joint, the bones of your humerus and ulna. And then the force is, say you're lifting a barbell, is going to come from your biceps muscle, which is attached to your forearm. So the force is actually going to come from past the fulcrum. And then the load would be the barbell in your hand. So when we're using our levers, our work input, again, looking at that conservation of energy, has to match the work output. So let's look at this picture here. Let's say this load is 20 newtons, and when she pushes down on the lever, she's going to move this load a half a meter. If she moves her end of the lever 1 meter, how much force has she got to apply to move that 20 Newton load half a meter? Well, let's look at our problem. So we know our force times distance input has to equal our force times distance output. And so if we can say that the um, distance she's moving over here is 1 meter, so that'll be F times 1. And then we have our 20 Newton load over here that's going to move a half a meter. So we can just do the math out. And that will give us F is going to equal 10 newtons. So she only has to exert a force of 10 newtons over here to move the 20 Newton load over here. We can also do something similar with pulleys. And if we set up a pulley like we have this one set up in this picture, it's going to operate like a lever with equal arms, like a seesaw in a playground. So as she pulls down on the rope, she's going to do a certain force times distance input, and that's going to be equaled by the force times distance output pulling the box up on the right-hand side. So the force is going to be the same on both sides. The distance the box moves is going to be the same as the distance she pulls on the rope. But what's changed here is the direction of the input force. But what if we do want to lift more weight? Well, we can rearrange our pulleys and we can double the force of the output by lifting more weight. As we can see here, if we arrange the pulley like this, we can half the distance that we pull the rope. So of course our force has to double. So we can lift twice as much weight. And we can figure this out as our force times distance. If we half the distance, then we're going to have to double the force. So remember, the force times distance output can't be greater than the force times distance input. So no matter what kind of machine we have, if a machine multiplies force, then we're going to have less distance. And if we have a machine that increases distance, then we're going to have less force. Now, when we looked at levers, the examples we used were of what we call ideal machines. 100% of our input came out as 100% output. In real life, this absolutely does not happen. We do not have 100% efficient machines. Some of the energy is converted to heat and does not do useful work. But we can say the closer our output is to the input, the more efficient that machine is. So the percent we can express this efficiency as a percentage, and that's the percentage of the work put into a machine that's converted into useful work. So in equation form, our efficiency would be useful energy output divided by the total energy input we put into that machine. So let's say we have fuel that has 100 joules of energy, and we put that fuel into a machine, and then our machine does 30 joules of work. Which of these would you say is true? That 30% of the energy input did useful work and 70% was wasted? 70% of the energy input did useful work and 30% was wasted? Or neither, energy must be conserved? Well, the correct one here is A. Because we only got 30 joules of work out of our machine after putting in 100 joules of energy, we only got 30% efficiency. And the other 70% of that energy input was wasted, probably as heat. And while energy must be conserved, when we're talking about the conservation of energy, we can count both the 30% of useful work and also that 70% that was transformed into heat, because heat is also energy. But even though a lot of our machines waste energy, we can devise ways to try to capture that energy and use it so that it doesn't go to waste. For instance, in the 1880s, when Thomas Edison built some of the first electrical power plants in New York City, he used coal. His buildings, the power plants burned coal to create steam that drove turbines that created electricity. And so he actually piped this excess steam to buildings close to the power plant so they could use it for heat. And some large buildings in New York City today still use this kind of method. They gather excess heat from their on site power plants and use that to heat the building instead of it just being wasted in the atmosphere. Many homes in Denmark, for instance, are also heated by excess heat from power plants. And this would be a great source of energy for us, because in the United States, our fossil fuel power plants that burn either natural gas or oil or coal lose about 70% of that energy input to heat. So about 3/4 of the fossil fuel we're burning in these plants we're absolutely wasting. So our plants could be much more efficient. Our bodies are also a type of machine, so we need to feed it, we need to give it energy. Our cells feed on hydrocarbons, which we call carbohydrates, and these release energy when they react with oxygen in our cells, just like gasoline burned in an automobile engine. But if we look at the food we eat and then look at the product's metabolism, there's more energy stored in that food than there is product's metabolism. So where did all that extra energy go? And actually, a lot of the excess energy is released as heat. So think about when you exercise, and as you exercise, your muscle cells are contracting. Okay, your heart's pumping, and as these cells are contracting and pumping, they are using energy from our food, and some of that energy is used to contract the cell, but then a lot of it is wasted and it's released as extra heat. And this is where our body heat comes from, and also why you get really hot and sweaty when you work out, because your body temperature goes up because your muscles are releasing that extra energy as heat. Now, in some cases, if you have a whole lot more extra energy from your food than you're burning up, then that extra energy can also be stored as adipose tissue, but that's a whole nother story. One of the most basic sources of energy that we have is the sun. And the sun is the source of most of the energy that we use when we turn on a light switch or plug in our phone or whatever. For instance, sunlight works in the water cycle to evaporate water. That water then falls as rain, which flows into rivers. And we can harness these rivers to turn generator turbines and electrical power plants. And then the water goes back to the sea to repeat the cycle. Sunlight can also be transformed into electricity we can use by solar cells, photovoltaic cells. Also, heat from the sun is what causes wind. And in some areas of the world, this wind is consistent and strong enough that we can use it to turn generator turbines and get electrical power that way. And then light from the sun is also used by plants and stored as plant tissue, which is the basis for most of the animal food chain. Animals eat plants, and then larger animals eat those animals, and so on and so on. And more energy from the sun hits the earth in 1 hour of the average day than all the energy that we humans consume in an entire year. And I read an interesting article that some German researchers had done the calculations and figured we could build some large solar cells in the Sahara Desert, which, there's actually no one living in this area of the Sahara, and there's not a whole lot of wildlife or whatever. And we could build a large solar cell there, and it could power like something like 2 times all the energy every human being would need on this planet. So it would be interesting to see in the future if we can harness the sun to make that renewable, non-polluting energy. Some other sources of energy that we can use for our everyday needs are fuel cells like batteries. And broken down into its most basic form, this is a chemical reaction between hydrogen and oxygen that produces an electrical current, the movement of electrons, and we can use this to power, um, say, flashlights and things like that. We can also get energy from nuclear power, and nuclear power is stored in elements such as uranium and plutonium, and certain isotopes of these elements are unstable and their nucleus decays. And as that nucleus decays, it releases radioactive particles and also electromagnetic radiation that we can harness for energy. And we can also harness the geothermal power, the heat from the Earth's interior. There are several countries, such as Iceland, that use this quite extensively for both electrical power and for heating homes and other purposes.